Yes, this is Gabi Emmanuel presenting memory management in operating systems, as it is one of the functions of the operating systems. We shall start with the background of memory management. A computer system can be abstractly viewed as the CPU, the memory. The efficiency of the computer depends on how its memory is organized and accessed by the CPU. The efficiency of a computer can be graded depending on the following traits or characteristics. Have access time. This is the time it takes the processor to locate programs in the memory. Size of the memory. This is how much data the memory can store. So functions of the memory management unit as the part of or as the core component of memory management. It provides microprocessor with virtual memory. It takes care of allocation and reallocation of memory to programs, memory allocation techniques, memory allocation information updates. It provides memory protection and sharing. So we shall be looking at virtual memory in details. Virtual memory is a method that computers use to manage storage space system running quickly and efficiently. Virtual memory gives an illusion to the program that a huge amount of memory is available for waiting and executing programs greater than the size of the physical address available. So virtual memory, like for the Linux system, when you are installing the Linux system, they ask you to create a swap space. That swap partition you create acts as the virtual memory of your operating system, in that when the physical RAM that the hardware part of the computer has gets full while executing programs, that swap space can keep programs waiting for a free space in the physical RAM. So the advantages of virtual memory can be system libraries can be shared. Only part of the program needs to be in the memory for execution, not all the programs. Logical address space can therefore be larger than the physical address space. Allows address space to be shared by several processes. Allows more efficient process creation. And this will be explaining how virtual memory really works. This diagram on the left shows the computer without virtual memory. Suppose page 1 requests for a storage space in the physical RAM. Page 0, they assign it a portion of the RAM. Page 1, they assign it a portion in the RAM. And page 2, suppose this is the space of the physical RAM, the total amount of storage the physical RAM has. Now if process 3 requests for space in the RAM, it won't be available since it is full. So for that reason, the computer might crash. And on the right, we have a computer with, or a system with virtual memory. So if page 1 requests for a space in the RAM, it is mapped onto the RAM. Page 1, the same thing, and page 2, they map it onto the portion. It's not the way this one is, they just map it anyhowly. And if page 3 requests for space in the physical RAM, the fact that RAM is full, they will first keep that request or that process in the virtual memory. This acts as the virtual memory. So if this one is processed successfully and this space is free, or not, this one will be shifted onto the RAM, and it is executed. If this one is not free yet, or it is not done, so long as it was the first one to request, they will keep it in the virtual memory, and page 3 will be executed, and that continues. So if this portion was the second to be assigned to any request this side, they will shift it down, and the page which is here will be shifted for partial processing, like that, and the sequence continues. Now, as we used page in this slide, here paging, we shall be looking into paging in details. Paging is of two types, that is the pure demand and the prefetched demand paging. Paging is a memory that executes strategy in which process is added is broken into squares of similar sizes called pages. Yeah, as you can see here, they are broken down into squares of similar sizes. They can be of 251 bytes, 8192 bytes, depending on the architecture of the system. It allows processes to fit the memory and to be running at the same time. It allows the pages that are being referenced actively to be stored in the memory. Yeah, these diagrams show you, like as I said in the previous slide, this one is mapping to the virtual memory in this container, and this is the physical memory. So when request, the way I explained it in the other slide, it is the same way here. And here also, this one just shifting. Here page 3 was in the virtual memory, but afterwards page 0, which has been here, it was partial processed, then it is shifted into the virtual memory in this diagram. Then page 3 that was in the virtual memory is shifted to the physical memory, and that process continues like that until all the processing is done. Now swapping. Yeah, swapping is a system in which a procedure can be swapped briefly and primary memory or move to optional capacity oplets and make the memory accessible to different procedures. At some later time, the framework swaps back the procedure from the optional stockpiling to principal memory. So this is all about swapping. The way I explained it here, just swapping pages from the physical memory to the virtual memory, processing it, doing it over and over again. Then memory allocation. Memory allocation is the way towards doling out squares of memory on solicitation. Regularly, the allocator gets memory from the working framework in the few substantial abstracts that must partition up to fulfill the solicitation. For little squares, there are 3 memory allocations or memory allocation types. That is the first fit, best fit, and worst fit. First fit allocates the new process in the first hole in which the process will be fit. Best fit allocates the new process to the smallest hole that is big enough to hold the process. Worst fit allocates the new process to the largest hole available. So this takes us to the advantages and disadvantages of paging. Yep, as mentioned before, paging decreases the outer discontinuity, yet at the same time experience the ill effect of inside fracture. Like it decreases the probability of our systems to crash. That is discontinuity. Paging is easy to actualize and expected as productive memory for the board method. Due to the parallel side of the pages and edges, swapping turns out to be simple. Yep, swapping and paging works hand in hand. Yeah, page table requires additional memory space, so may not be useful for framework having little RAM. Yeah, you see, the last point is a disadvantage of paging, since it requires additional memory. As I said, for Linux users, they have to get a partition on their hard disk to call it the swap space. So that additional memory space needed might not be always available. Okay, continue. Now this brings us to segmentation. After virtual memory, we saw that the memory management unit provides segmentation, and segmentation, the virtual address with segmentation, the virtual address space is partitioned into segments of different lengths. This leads to a creation of fragments. The fragments are of two types: external fragments and internal fragments, as I've explained them here. All-out space is sufficient to fulfill a solicitation or dual procedure in it. However, it isn't adjacent, so it can't be utilized. Internal fragmentation, memory square appointed to the process is greater. Some part of the memory is left unused, and it can't be utilized by another procedure. Okay, that is the explanation of those two types of fragments which come after segmentations. Here are two types, two tables that are used in segmentation and page tables. These are segment and page tables. There are two types: segment and page tables. Segment table contains information about every segment. Each segment table entry point to a page table entry. Memory sharing and protection. Memory protection as one of the functions of memory management or of the operating system. Memory protection is the capacity of the hardware to prevent programs from accessing another program's memory, except under careful controlled conditions. Now, what is sharing? Memory sharing is possible with segmentation, as it provides a mechanism to completely isolate users from each other by giving each user its own virtual address space. Yep, techniques of this include, like sharing, they just segment the memory, then they assign each user different portions of the memory, in that those different users, they can't interrupt with another user's partition of the memory or portion of the memory, and that promotes security or memory protection. So techniques of sharing include address generation. This method Address generation. Just this method places pointers to shared segment in all segment tables at the same effort. So one segment number can be generated when a virtual cache is used by the sharing of or during sharing of data. It can give a consistency problem. When two different virtual addresses are mapped at the same physical space, they can reside at two different cache entries. Despite the purpose of having shared address, modification to cache entry are not visible to another entry. Despite the purpose of having shared address, modification can not be visible to another entry. Sorry for that, this is a repetition, and that drives us into data exchange as part of sharing. Common data exchange is of two categories: commonly addressable storage and separately addressable storage. Here, in commonly addressable storage, each user has access to only one address space, and in separate desirable storage, each user has its own address space maintained by its own segment table. As you are seeing in this diagram, here these are pages, they are sharing the memory. So each user here has a portion. Each user has a portion in the memory. So this brings us to dynamic relocation. Dynamic relocation, in this method, the hardware adds relocation register, the virtual address generated by the compiler. The relocation register allows translation to a physical memory address. Hardware compares this memory address with the limit register. If the memory address is higher than the limit, the processor takes an address trap and ignores the physical address. It requires two special registers, a simple addition and a simple comparison. Its advantages may include: a processor can grow over time because it can easily be relocated from a larger memory block. So this brings us to protection as another function of the operating system under memory management. Protection. This is a way to control memory access rights on a computer. The access matrix model gives a way to describe the protection system. The state of the system is defined by OS, object, subject, and addressing. Memory protection uses the following techniques. This is for access: object, subject, access, and it uses the following techniques. Access list. The access list associates with the object, contains the pair. The access matrix is stored by column. For each non-zero element in a column, the corresponding object has on the object are put in a case list. Like here, this is an example of an access list whereby this user has, these are the rights they have. These are the rights they have. They can, user B can read, user S can read and write, user A can write and write, user A can read and write, as it is here. Yep, that is an access list. Yep, this brings us to the capability list as one of the techniques used during memory protection. Capability list, the access matrix is stored by laws known as capabilities. Each subject has the right it has for an object stored as a pair of cache. Another technique they use is a key lock matching system. This system uses both capability list and the access list. So this is the steps followed during memory protection, or one of the logics behind memory protection. Step 1, you access or a request is made. In step 2, they scan the attributes to determine whether they match with the existing policies. Like they check if you have the permissions, or in the access list here they are called the access rights, or you have the access rights to do a specific action. That is in step 2. Then in step 3, if the attribute match a policy, the system allows access to the user. Like if you have the privilege to do what you are requesting, then the system will grant you access. Yeah. So for more information, you can visit these sites where my content was obtained. Thank you.